In this next section, we're going to talk about differential equations. Now, differential equations we've already looked at when we first started talking about antiderivatives. And basically it says that if I have the derivative of a function and I integrate, I want to come back to the original function. Okay? A differential equation is just that. It's solving an equation that involves the derivative of some unknown function. And so we have basically two types of solutions that we're going to look for. This first is basically what we've done with all of our integration, the first step to our integration, and that's the general solution. The general solution of a differential equation is the general antiderivative of the function. So in other words, if y equals f of x dx, then y is some capital F of x plus c, where f prime, capital F prime, is little f of x. So this is just saying that if I've got the derivative, then I can simply take the antiderivative, and there's my general solution. Again, you have to have that plus c on there for that general solution. The particular solution of a differential equation is a specific antiderivative that is based on some initial conditions. And so this is a little bit this is a little bit more like what we did with definite integrals. So if I know that dy is equal to f of x dx, where y of x naught is equal to y naught, then y equals some f of x plus k, capital F of x again being our antiderivative, but k being a specific value based on these initial conditions. And that k is going to come out to be some real number. Okay? So all of the derivatives or antiderivatives that we've done up till now fall into one of these two categories. And so this section becomes a little bit different because we're going to talk about a specific type of differential equation. Okay? And that's what we call a separable differential equation. This is one in which the equation can be rewritten so that there is exactly one variable on each side of the equation. Okay? And again, if we look back in our previous notation, that's kind of what we're talking about here. It's just our equations are going to look a little bit more involved. And so the idea is to solve this differential. Again, what we'll do is we'll separate the variables. So if I have dy dx on one side or y prime on one side, and some expression that contains both x's and y's, then I want to separate it out so there's a function of y dy equal to some function of x dx. And then the idea from there is I can integrate, get those antiderivatives, and then find my solution. In this case, we're looking at dy dx is equal to e to the x y cubed. Okay? And here again, if I look, I've got x's and y's on both sides of the equation. So again, the first thing I want to do is separate these out so that I have x's on one side and y's on the other. Okay? So to do that, I'm going to divide out by y cubed and multiply by dx. Okay? So here again, the integral of 1 over y cubed dy is going to equal the integral of e to the x dx. Taking my antiderivative of both sides, so here again I can think y to the negative 3, so we'll get a y to the negative 2 divided by negative 2, or a negative 1/2. Again, the constant we'll put on the other side. Integral of e to the x dx is e to the x plus our constant. Okay. Again, we're not quite done because again we want to solve for y. So we need to get that y by itself. So here we'll multiply through by negative 2. And then here, this is where it gets a little tricky. If I look at this, I can't just square root both sides because that's a negative 2. So this is actually saying 1 over y squared is equal to negative 2 e to the x minus 2c. So one of the things I can do is reciprocate both sides. So y squared will equal 1 over negative 2 e to the x minus 2c. And now I can square root both sides. So again, the square root will give me that plus or minus 1 over negative 2e to the x. The negative 2c, again, is just some constant. So I'm just going to call it d. Okay. Now, in all of these, if you want to start with some other variable for your constant of integration and then work it out so that's a plus c at the end, that's fine. Most of these problems, if you're looking at the practice problems or even the solutions in WebAssign, they're always going to leave it with the c here. But you should recognize that if you put c here, the c is very different from the c. And so you should make note of that somewhere. When you go to write your solutions in WebAssign, you are likely going to want to put the c in here. So again, you can treat this as d all the way down and then rewrite it as c. In these next two examples, we're going to look at a couple more separable functions, but now we're going to look at ones with initial conditions. And in these examples, these are going to be a little bit more involved than the last two that we looked at. Okay. So in this first one, we have that dy dx is equal to e to the x minus y, and we have the initial condition that y of 0 is 0. We want to solve for y. Now, unlike the last one, I can't just divide out right away because, again, I have x's and y's on both sides. So here we need to use some exponential properties to rewrite. So dy dx, e to the x minus y is the same as e to the x divided by e to the y. So then we can see that multiplying by e to the y and multiplying by e to the x will help us separate our variables. Okay. From there, we're going to integrate both sides. So the integral of e to the y is e to the y. Integral of e to the x is the e to the x plus c. Okay. Now here, because I have initial conditions, before I try to solve for y, I want to plug in those initial conditions. And the reason I want to do it at this step and not at the end is because here it's going to be a little easier to solve for c than if I try to move everything over and take natural logs and then plug in. Okay? So here, I'm going to plug in initial conditions. Okay? So our initial conditions say when x is 0, y is going to be 0. So e to the 0 will equal e to the 0 plus c, which just tells me 1 equals 1 plus c, or c is equal to 0. Okay? That makes this very nice. That means when I go back to my equation here, e to the y will equal e to the x plus 0. So taking the natural log of both sides, I can then solve for my y, so y will just equal x. Okay. There's my particular solution to that differential equation. Okay. All right, so let's look at another example. In this example, we have x squared dy dx plus 1 over y squared equals 0, with the initial condition that y of 1 is equal to 2. Okay. So again, the first thing I want to do is separate my variables. Now this one's even a little trickier because now I've got dy dx plus something. So again, the first thing I'm going to do is start by rewriting. I want to get this dy dx term by itself, so I'm going to subtract over the 1 over y squared. And now I can multiply and divide things. So again, I want the y's on the left, so I'm going to multiply by a y squared. And I'm going to divide out by x squared and multiply by dx. Oops. I said that right. Divide out by x squared, multiply by dx. Okay. So now that my y's and x's are separated, I can go ahead and integrate. So finding the antiderivative here is a 1/3 y cubed Again, the constant will go on the other side. Here, my antiderivative, if I look at this as x to the negative 2, I'll get an x to the negative 1 times the negative 1, so this is just 1 over x plus my constant. Again, at this stage, plug in my initial conditions. Okay, so when x is 1, we see that y is going to be 2. So 1/3 of 2 cubed has to equal 1 over 1 plus c. So 8/3 will equal 1 plus c, or 5/3 will equal c. So there's what our constant of integration is. So now we plug back in. So we're going to plug this back into the solution. So we're going to get a 1/3 y cubed equals 1 over x plus 5/3. Now again, here we're not done. In order to solve this, we need to have y by itself. So I'm going to multiply both sides by 3. So we'll get y cubed is equal to 3 over x plus 5. And then to get y by itself, we can cube root everything. Notice cube rooting, no plus or minus. So there would be our particular solution for that differential equation.